Okay, we're back, and we're going back to forces of friction, which we already talked about because we had to talk about it for the lab, but we'll try to get through it pretty quickly because I want to talk about circular motion because that's what we're going to be doing in the lab. And I knew, somebody pointed out to me, the lab is not posted, I guess, but I'll make sure it's posted before we actually have to start the lab. So that gives me 2 hours to get that done. What? It's posted? Okay.
Yeah, I got in my packet.
Okay, it's circular motion, right?
Mm-hmm.
Okay.
Yeah.
Okay, good. At this point in the semester, the way that things are going, I'm like, I just assume that I screwed up at this point. But normally, historically, I've been better at being on top of things, and I apologize. It's just like absolute chaos for some reason. But that's basically been every semester since 2020. So someday I will get back to being a normal, competent person. But also, like, this is new. And it's kind of exciting, and the videos, I think, are coming out better. So how many of you actually watch the videos? Do you like them?
Yeah.
Do you have any?
They're very concise.
Do you have any feedback? Do you want anything else?
Keep making them.
Keep making the videos. Okay. I'm going to try to start putting in extra example problem videos, but that's as if I have time, because as you can see, doing a problem takes a long time even if you know how to do it. And it takes even longer if you don't know how to start it. So let's talk a little bit about friction. Remember, friction is caused by interactions at the molecular level and the relationship between friction and normal force. And remember, sometimes I write normal forces in lowercase n because I forget, and they're all the same. So, like, remember, normal force can be written 3 ways, and I tell you this because if you look at YouTube videos or other books, the nomenclature isn't consistent. So normal force is either capital N, lowercase n, or F sub n, okay? And when I say sub, I mean subscript, so the little tiny n that's below it. So kinetic frictional force is equal to the coefficient of kinetic friction times normal force. Now remember, the interesting thing about this equation is, one, these are not vectors, because remember, friction, kinetic friction is always perpendicular to normal force, okay? So we never write this equation with vectors because they would never be parallel. The other interesting thing is, remember, this has no dimensions, right? Meaning no units, because remember, you're going from a force to a force, but there's a relationship here, and the other thing is that there's no variable, right? Once you have a constant normal force, you have a constant friction. So friction doesn't depend on speed, doesn't depend on acceleration. It only depends on normal force and the materials that are in contact, okay? So we're going to do a quick example problem. We have a crate that we're pushing on with a force of 50 newtons. So we push on a 10 kilogram crate with a force of 50 newtons across the floor that has a coefficient of friction of 0.3, and we want to know the acceleration of the crate. So we're going to start. Do we expect it to have a lot of acceleration?
Mm-hmm.
So what range would we guess? Like 0 to 1, 1 to 10?
Yeah.
Like 1 to 10? Okay. So we're going to say we're going to guess acceleration. Acceleration is between 1 meter per second squared to 10 meters per second squared, and probably closer to 1, okay? So let me just draw the picture. So here's our floor. Oh, that's really crooked. Sorry. It's a lot of pressure when you know people are going to see this video to, like, make the drawing not suck. Okay, so here's our crate. What are the forces acting on this crate?
Normal.
Normal force. Pushing force, we'll call this F push. Probably weight, right? Anything else?
Friction.
Yeah, friction's pretty important. So we'll say friction, and it's kinetic friction, okay? So 10 kilogram crate, perfect. We can draw this in a free body diagram or not. Coordinate system, do you think we have to worry about the coordinate system here? No, it's pretty standard. So this is a standard XY coordinate system. I'm going to skip drawing the free body diagram just because I think it's not necessary here, and this is a place where you could also not take the time to do that. But if you feel like you still need to do that to sort of get your brain around the variables and the forces, go ahead. Which way do we think the acceleration is? Yeah, direction of F push, okay? Because remember, friction is never bigger than the pushing force. It can be equal or less. So, what do we want to do next? What equation do we use?
Well, we just did
Newton's second law. And also, also we want to know that we use this one, right? We know this one. And then we use Newton's second law, so Newton's, which means we're summing up the forces in the x and y direction. So we'll start with y because it's easier. That means normal force minus mg is equal to mass times acceleration in the y direction. But what's the acceleration in the y direction? 0. And then we sum up our forces in the x direction, which is F push minus kinetic friction is equal to mass times acceleration. Okay, so we have, in this case, 3 equations. 1, 2, 3. How many unknowns do we have? Well, we don't know acceleration, right? We don't know friction, right?
Normal force.
And we don't know normal force. But we know everything else. So we have 3 equations, 3 unknowns. Can we solve? Yes. System of equations rules say, yay, we can solve. So we start plugging stuff in. We start with this equation and we say, okay, F push minus mu k n, all right, is equal to mass times acceleration. But remember, from this equation, we get n is equal to mg. So we can say F push is equal to mu k. Oops, sorry, not equal. That's a minus. Minus mu k, the coefficient of kinetic friction, mg is equal to ma. All right, so we just solve for acceleration, and that means we have F push minus mu k mg divided by mass. So we just plug in numbers. So that is going to be 50 newtons minus 0.3. I'm going to write 0 mu k is equal to 0.3 on our picture, just for reference. The mass is 10 kilograms, 9.8 meters per second squared. Sorry, that got kind of gnarly in there. And 10 kilograms. So you plug all that stuff in, and we end up with 2.1 meters per second squared. Is that anything like what we predicted? Yeah, it's between 1 and 10, and so we did a good prediction. Okay. Do you want me to zoom in on that? There's some squinting happening. Here. There. Math zoom. So that was kinetic friction. Remember, for static friction, what is the relationship for static friction? What is static friction equal to? Okay, what's the maximum static friction equal to? Yeah, so the static friction coefficient times the normal force, right? But that's just the maximum static friction. But remember, we did a whole demo. If you're pushing on something, I guess this. So, oh, that's nice and heavy. So if I'm pushing on this, right? If it's not moving, if I push, what's the static frictional? If I push this way, what's the static frictional force that way? The same amount that I'm pushing, because remember the whole key to static friction is that it's not moving, so that means the acceleration has to be 0. So if I push with 1 Newton, static friction has to be 1 Newton. If I push with 2 newtons, static friction has to be 2 newtons until you get to static friction max. So a lot of these problems deal with the maximum static friction, but it's a key point to remember that until you reach the maximum, right, until right before it starts moving, it's just equal to the pushing force, okay? Just making sure that thing's on me. Okay, so static friction force equal to the pushing force until you get to static friction max, okay? Once you exceed the maximum static friction, then what happens? It starts to move, and then you switch to what kind of friction? kinetic friction, okay? And so because of this, the coefficient of static friction should always be greater than the coefficient of kinetic friction for two of the same materials, okay? And remember, friction is just the interaction between two materials. Sorry, we had this whole thing. And we have this relationship where, here you're applying 1 Newton, right? And that means friction is 1 Newton and 2 newtons, and friction is 2 newtons. You apply 3 newtons, friction is 3 newtons. You get to the maximum, let's say 5 newtons, and then you have this little curve where you're starting to move. It's that sort of, there's an elasticity thing happening there, and then it becomes kinetic friction, and it's just constant. Okay, so it doesn't matter how much harder you push, the friction remains the same. Okay, for kinetic friction, you can apply more pushing force. It doesn't change the friction. All right, so we're going to try another friction problem, but in this case, and I'll have you guys start this, but in the interest of time, we'll go over it pretty quickly. We're pushing on a 10-kilogram crate with a force of 50 newtons once again. In this case, the coefficient of static friction between the crate and the floor is 0.6. The coefficient of kinetic friction between the crate and the floor is 0.3, and we want to know what the force of friction is acting on the crate. But what we don't know is if the crate is moving or not, okay? So how do we decide if the crate's going to move? And then if the crate's if the crate's not moving, we know, how do we figure out what the friction force is? And if the crate is moving, how do we figure out what the friction force is, right? So it's got sort of a flow chart situation here. So how do we decide if this crate's moving or not? Yes?
By finding the max static friction,
Yeah, and then comparing it to what?
the minimum kinetic friction.
Not quite, right? So what force are you pushing with? Okay, so let's say the maximum static friction is 49 newtons. Are we moving or not moving? We're moving, right? So if we push with if our maximum static friction is 49 newtons and we push with 50, then it moves. If we push with 48, then it doesn't move, okay? So the first thing you want to do is calculate the maximum static friction, and then you want to compare it to your pushing force. If you're pushing harder than maximum static friction, then you switch to kinetic. If you're pushing less hard than maximum static friction, what is your frictional force?
Same as your normal force?
Same as your pushing force. What's your pushing force? 50. So if it's not moving, then the answer is 50 newtons. But we have to decide if it's moving or not before we can say that. Okay, do we understand that? All right, I'm going to set it up and do it, but go ahead and try to determine the maximum static friction. So let's go over this problem. We're going to start by drawing the picture because we need to know the forces in order to calculate the static friction force. So it's going to look a lot like the previous picture. In fact, I'm going to just copy it from the previous picture. All right. The only thing we have to change is there's not acceleration. We don't know which friction this is, and we also know that the static friction is 0.6. So those are all slightly different. Let me just move this over so we have space. So I'll call that those things. Okay. So if we want to calculate the maximum static friction, that's mu s n. What's n in this case? How do we solve for n? Yeah, it's just going to be mg because when we sum up the forces in the y direction, it's n minus mg equals 0, okay? Which means n equals mg. I'm not going to go through the whole rigmarole every time. We've been doing that a lot. So I'm going to call this n equals mg, okay? It's not always true, but it's true in this case by just looking at this and knowing there's no acceleration in the y direction. So that means our static friction max is mu s mg. So we can plug in numbers. That's 0.6 times the mass, which is 10 kilograms, times 9.8 meters per second squared. So if you just wanted to estimate this, you'd say, okay, 10 times 10 is 100 times 0.6 is 60. So it's probably, the max static friction is probably bigger than 50. If you actually plug everything in, it gets 59 newtons, okay? So remember, this is our maximum static friction of 59 newtons. Are we moving or not moving?
Not moving.
Not moving, because we're pushing with 50 and our maximum is 59. So how hard do we have to push to move this thing?
60.
Yeah, 59 newtons would work, 60 newtons would work. Anything above 15, equal to or greater than 59 newtons means that we're going to be moving. But because we are pushing with 50, we are not moving, okay? So that means this friction is, this friction is static friction, but it's not at the max. So what is our force of static friction? 50 newtons, right? Because if we sum up all our forces in the x direction, that's going to be F push minus static friction is equal to 0, which means F push is equal to static friction, and we know that F push is 50, so force of static friction is 50 newtons because we have not reached the maximum static friction yet. All right? Yes?
Is it 0 because it's not accelerating?
Right, because it's static. So if it's not moving, that means our acceleration is equal to 0. Okay? How would we have calculated the frictional force if we were pushing with 60 newtons?
Use the kinetic coefficient, the normal force.
Right. So you would say, so if we were pushing with 60 newtons, that means we know we would be moving, and we could use this equation, Fk is equal to mu k n, which in that case would be mu k mg. So probably about 30-ish newtons, because it would be 10 kilograms times 9.8 times 0.3. Okay, so kinetic friction would be approximately 30 newtons, and that's for any amount of pushing greater than 59. So I could push with 100 newtons, and this kinetic friction would still be 30. That's what I mean by kinetic friction does not depend on the pushing force. Okay. Okay. Cool. Called the angle of repose, which is really just a good name for a band. But basically so remember, friction is the microscopic interactions between two materials, okay? So if you have granular things like sand, that's made of one material that rubs against itself. Even though they're very small pieces, they still are macroscopic from our perspective because we're not at the atomic level. So every granular material has its own angle of repose, meaning if you make a little mountain out of it, it will, the angle that mountain has at its peak is going to be dependent on the material of the grains that you're using. So for instance, dry sand has an angle of 32 degrees, soil 45, wet soil is 34, sugar is 34, and rice is 40 degrees. How do you decide if it's going to be pointier? What would the coefficient of friction be? Bigger or smaller for pointier peaks? Bigger, right? To get a steeper angle of repose, you need more friction, right? So stickier things can come to a sharper peak. If it's really slippery, then it kind of flattens out, okay? So just a fun side concept. So very much like what we did in the friction lab, this one talks about the maximum angle upon which a wooden box can sit on a wooden ramp without sliding. So in this case, the coefficient of static friction between the objects is 0.5, and the coefficient of kinetic friction between objects is 0.2. What we need here is to set up our forces. So we'll start once again by drawing our forces, and we're looking for the angle. So if you're thinking about what we need to think about, we want maximum, let's make that purple. We want maximum angle. So we want to start by drawing our forces. We have normal force pointing in this direction. We have weight mg pointing down, and we have static friction pointed in this direction, and we know static friction is equal to, static friction is equal to the component in the opposite direction if it's not moving. So we want to set up our coordinate system to be in the direction of, let's say, anticipated acceleration in this case. So we'll do this XY coordinate system, which means whatever this angle theta is, oops, we'll make it purple. We're going to need that to split these mg sine and cosine of theta. You can see this angle theta should be the same as this angle theta. And so this will be the adjacent side. This is mg cosine theta. This is mg sine theta. Okay. Now that we have all of our forces, you can draw these on a free body diagram if you would like. So I'll just do that really quick. Hopefully this is lined up to scale. So you have x, y, we have this dot. And now we can, let's just keep the ones we're going to use. So this is normal force. This is static friction. This is mg cosine theta. And this is mg sine theta. And since we know that this is a static problem, we're going to do this until essentially this starts moving. And it's going to start moving right when mg cosine theta is equal to the maximum static friction. So remember, we know that the maximum static friction is equal to mu s n, whereas regular static friction, if you haven't reached the maximum, is just equal to the opposite force. So in that case, it would be mg sine theta. So in order to calculate this, we just want to use Newton's second law, which is force equals mass times acceleration. But of course, we want to do this in the x direction. That would be mg sine theta minus fs max is equal to 0. And in the y direction, we have normal force minus mg cosine theta equals 0. Now remember, both these zeros are mass times acceleration, but because this is a static problem, they're just acceleration. We're looking for the angle, so obviously we don't know what the angle is, but we also don't seem to know some other things. So we don't know normal force. And we don't know, I believe, we don't know Fs max, obviously. And we don't know mass. Or do we? So we're going to have to hope that cancels, because we have 3 equations and 3 unknowns we're solving for theta. So let's start by rearranging things. We know from this equation that n equals mg cosine theta, so we can plug that in up here. So we know that Fs max is equal to mu s mg cosine theta, and that needs to be plugged into this equation here. So we end up with mg cosine, rewriting this equation. Mg sine theta is equal to Fs max, but that's mu s mg cosine theta. The nice thing about that is, remember, we had this 4th unknown, which is mass, but that's going to cancel. So we're going to cancel out mass. And then we'll solve this for angle. That's going to take a couple steps. So that becomes, we can also get rid of g. Sorry. We'll also cancel g. And so we end up with mu s is equal to sine over cosine, so tangent theta. But unlike in the lab, instead of finding the angle and then looking for the coefficient of static friction, we're going to do the opposite. So theta is going to be tangent inverse of mu s. So that's going to be tangent inverse of 0.5. Remember, we're using the coefficient of static friction, not the coefficient of kinetic friction. And that should give us a value of 26.6 degrees. Pro tip, you're going to want to make sure that your calculator is in degrees if you want your answer in degrees, and radians if you want your answer in radians. And we switch back and forth in this class, so it's something you're going to need to keep track of. Rolling friction is a special case of static friction. So when you're driving a car or riding a bike, the way wheels work is that the part that comes in contact with the ground or whatever you're rolling on, that part doesn't move. Everything else in the wheel is moving, but at that point that it's hitting the ground, it's not moving, and that's where the static friction happens. So the wheel turns this way. If we have a force that's propelling the wheel, it goes this way, and static friction goes in the same direction as propulsion. Now this will make a little bit more sense when we get to torque, and you'll see why I drew these things the way they were drawn. But the normal force would be here, because that's where the wheel comes in contact with the road. And then the weight acts at the center of mass, which is something we'll talk about when we get to torque, okay? So why does friction point that way? Well, what happens if you push this wheel and it doesn't roll? Yeah, if there's no friction, it just slides, right? It just slides and it doesn't rotate, okay? So the friction is resisting that motion. So as the wheel rolls this way, the friction has to point the other way, okay? But it is static friction. Okay, so here we're going to add some kinematics back into this. We have a 5 kilogram crate, so let's just go through and get our numbers. I'll make that purple. 5 kilogram crate. It has an initial velocity of 2 meters per second as it slides down. Let's make that pink, a 20-degree angle ramp with a coefficient of kinetic friction of 0.5 and a coefficient of static friction of 0.9. So part A, we're going to draw a free body diagram. Part B, we're going to write the net force equation. Part C, we're going to find the acceleration of the crate. And then part D, we're going to do some kinematics and calculate how long it takes the crate to come to rest. So starting with part A, we'll start by just drawing our force diagram. So of course this is a ramp. We have our mg and our normal force. We have our static friction, and we know this is probably a tilted axis. So we'll call this X and this Y, meaning that we're going to want to break our mg into cosine and sine. Remember, if we have an angle of 20 degrees here, that's probably the same as 20 degrees here, because remember, if you want to do this as a triangle, right, this is a right triangle. That means this is 90, which means this is 90 minus 20, which is 70, which means since this is 90, this is 20. So all of that just to get the idea that this angle and this angle are the same, so this would be 20. That means that when we break this up into components along our coordinate system, this becomes mg sine theta, because it's the side that's not near the angle that we know, and this is mg cosine theta, where theta is 20 degrees. If you want to draw this as a free body diagram, you can draw it tilted or straight up, whatever you want to do. So you just draw the same thing. And then you just draw your dot and you say, okay, N, Fs, mg cosine theta, mg sine theta. Okay, so that's part A. Let me just move A over here. For part B, we want to write the net force equations. So our net force equations are just summing up in the directions of x and y. So in the y direction, we have normal force minus mg cosine theta, which is equal to 0 because there's no acceleration in the y direction. There's actually no acceleration in the x direction either because, oh wait, is this static or kinetic friction? Well, this is probably kinetic friction because it's moving, so that's different. So we'll call this kinetic friction. So we should have some acceleration in the x direction. And because this thing is starting out at a speed and going to 0, our acceleration is going to point in this direction. So just keep in mind, because I drew the x direction this way, acceleration is going to be negative, because remember we have an initial speed going this way, and it's slowing down to, at the end, v equals 0. So that means we have to stop, which means our acceleration has to be in the opposite direction. Okay. So that's our y direction, and that just means that n is equal to mg cosine theta. We'll just do some algebra now to save time later. And then if you sum up your forces in the x direction, you get mg sine theta. Remember, this is the positive x direction. And then minus frictional kinetic is equal to mass times acceleration in the x direction, but that's the only acceleration. And the only thing we know it's going to be negative, but our answer should be negative when we plug in our numbers. We don't have to do the negative sign now. Just keep track of it at the end before we plug it into kinematics. We should get a negative value. Okay. The only other thing we need to know is that the coefficient of kinetic friction times normal force gives us the kinetic friction. So we don't need the static friction coefficient. We only need the kinetic friction coefficient. Okay. So solving for this, I mean, we drew the net force equations. So solving for acceleration, that's going to be mg sine theta. We're just using this equation right above us, minus mu k n, but we know n is going to be mg cosine theta. Sorry, I used two different n's here, but let me just fix that. Mg cosine theta is equal to mass times acceleration. You'll notice there's an m in each term, so we're going to cancel out all of the m's so we don't have to use them this whole time. And it simplifies it, especially since we're given mass, but we don't actually need it. So let me just do those. I should do those in purple. Sometimes you're given more information than you need. That's a much better situation than being given less information than you need. So when we solve for acceleration, I'm just rearranging this, we get g sine theta minus mu k cosine theta. Okay, and we can plug in numbers for this. I like to line up my equal signs if I can, but we're running out of space. So that's 9.8 meters per second squared. And you'll notice this is just going to be g times something less than 1, because remember sine and cosine theta and mu k, those are all less than 1, so it should be less than g, so less than 9.8 if you're looking for something. And almost always our accelerations, when we're dealing with the primary force is gravity, but there's other things going on, is going to be less than g, so this makes sense. So we say sine of 20 degrees minus 0.5 cosine of 20 degrees. Plug all that stuff in, and that should give you negative 1.24 meters per second squared. So that keeps our negative sign that we were expecting. Since we did not put that into the equation, we were just guessing the direction. So you get it straight from the math because you put all the other signs in correctly. And that also means that when we do the kinematics part of the equation, we should get something reasonable. So let me just make this a little smaller so we have room to do some kinematics. And we'll go to part D, which asks us the time. And so in order to get the time, well, we know the acceleration, we know initial velocity, and we know final velocity. So we probably want to use this equation. And if we solve for this, that means time. Solve for time. So V final minus V initial is divided by A is equal to time. So time is equal to 0 minus 2 meters per second divided by negative 1.24 meters, or sorry, seconds. No, meters per second squared. You can see with the units, you'll cancel out meters, you'll cancel out 1 of the seconds, and you should end up with 1 over seconds, which is good. That'll give us seconds, and that gives us a time of 1.61 seconds. Which is a pretty reasonable time, and that's all we got. So remember, we're still just setting up free body diagrams, and then we're using our Newton's second law force equations to solve for acceleration, and then plugging in acceleration to our kinematics and being strategic about which kinematics equation we use. Since we've done some friction problems, but if you need more friction examples, I will have those recorded and posted by next week, okay? But I really want to get to circular motion because that's what the lab is on today, so it'd be nice if you knew something about that before we get started. Side note, what do we call friction in a fluid, or with like air or water?
Air resistance.
Drag, yeah, air resistance or drag. So this guy is old now. But anyway, this is an application of drag, and you'll see what I'll show you where this drag force coefficient comes into play. So remember, kinetic friction, really simple. Coefficient of friction, which comes from the materials times normal force, always constant, does not depend on speed, it does not depend on pushing force, just doesn't depend on anything, okay? Drag force is like friction, and it opposes motion, but it's a much uglier equation, okay? So here's the equation. This is the force of drag. This is 1/2. This is something called the drag coefficient, which depends on the details of the object shape. So the drag coefficient is usually 1/2. So you can almost always just write this as 1/4. But in the case of that speed suit that we saw on the previous slide, you can use good material science to like change the drag coefficient ever so slightly, which if you're trying to win a race will matter. So the drag coefficient, much like the coefficient of friction, can be adjusted if you get real creative. But for most cases, we just call this 0.5 as well, okay, unless otherwise told. This is the density of the fluid that you're in. So if you're in water, this would be the density of water. If you're in air, this would be the density of the air. And then this is the two most important things, the object's cross-sectional area, and we'll talk about what that means in a minute. And then the most important thing about drag is it depends on speed, right? So kinetic friction, you can push faster, that doesn't create more friction. For drag, when you go faster, there's more drag. And this is a very important concept if you are doing anything with like aerospace engineering. The faster you go, the more drag you have. So then you have to start adjusting these other things to reduce drag, which is why, if you have like a golf cart, it doesn't need to have streamlining. But if you have like some sort of fighter jet, it probably does. Okay? So things that go fast end up being more smooth shaped because that reduces the drag coefficient, and they use materials that are shinier for the most part because that reduces the drag coefficient. Because as you see, it's a square. So if you go a little bit faster, you get a lot more drag. Okay? Cool. Let's talk a little bit about cross-sectional area. So cross-sectional area, if you have a three-dimensional object, it's just if you sliced it this way, if you're moving this way, it's the slice this way. Okay, it's just the cutout shape. So for instance, I don't know if you've seen this delightful Japanese game show where people have to make the shape, like they're basically on a treadmill and it launches them towards this thing and they have to like make the shape or just get knocked over. Lots of fun. Cross-sectional area of a soccer ball, what is it?
Circle.
Just a circle, okay? Cross-sectional area of a cyclist, right? This is, if you're a cycling racer, that matters a lot because that changes your drag coefficient, which is why the road bikes put you in this uncomfortable hunched over position, because more cross-sectional area, less cross-sectional area. And then they also wear those like cool helmets that look like rocket ships. So that's all to reduce drag coefficient and to reduce the cross-sectional area, because all of the drag is force you're fighting against when you're on a bicycle. And if you want to get into like fluid dynamics, which is how the actual air behaves, then you can get into drafting, right, where you get in somebody's like wind shadow so that there's less air hitting you so you can go faster with less drag. Okay, we're not getting there yet, but cross-sectional area has a big impact on drag. And remember, we talked about free fall and we've been ignoring air resistance, but in free fall, air resistance does end up mattering, especially at higher speeds. So this brings us to something called terminal velocity. Okay, now terminal velocity means the point at which something falling reaches a constant velocity. So what does that tell us about the forces?
They're equal.
They're equal. So what's the force down?
Gravity.
Gravity. What's the force up?
Air resistance.
Drag, yeah, this thing that we call that's drag. So at some speed, right, this thing starts accelerating. It goes down faster and faster and faster. For every object at some speed, there's a speed that's fast enough where the drag matches the force due to gravity or the weight. Yes?
Is it dependent upon the weight of the object?
It depends on the weight of the object. It depends on the drag coefficient of the object, the cross-sectional area of the object as well. So every object is going to have a slightly different terminal velocity, but almost every object will reach terminal velocity if you let it fall long enough. Okay. Actually, some animals are good at understanding that intuitively, and so they change their cross-sectional area as they fall, like a wingsuit, basically, so that they slow down and reach terminal velocity sooner, right? So their terminal velocity is a smaller number, so when they hit the ground, they don't die. So anyway, how do we get constant speed? Well, we have to have our forces be equal. So if we drop a ball and it's not moving, there's no drag, okay? Once it starts moving, there's a small amount of speed. That means a small amount of drag, all right? And remember, the acceleration is g, but now that we have drag, our acceleration should be getting smaller than g because there's a net force that has an upward component, okay? So now the weight doesn't change, but as you go faster, the drag changes. That means the acceleration gets smaller, and eventually you'll have a situation where drag equals weight, and that means acceleration is 0, and that's where we have terminal velocity, okay? So we don't need to necessarily calculate these, but if you have all of these things, you can calculate terminal velocity. What I've done here is you're really just simplifying this. You change that drag coefficient to 1/2 and you solve for terminal velocity. Okay, so if you want to get terminal velocity for things, you just plug it into this equation. This is weight, this is just the cross-sectional area, and this includes both the drag coefficient and the 1/2. Okay, cool. All right, that brings us to what we actually are doing.